In this video, and paper linked in the description, I will explain how Pym particles are a miracle reaction agent capable of doing nuclear fusion at room temperature, destroy matter, leave a particle that carries all the information of the original matter so you can then reconstruct the original mass perfectly. All of this while being the key to solving world hunger, could be the death of humanity itself, and faster than light travel across multiverses. Or I guess a multiverse at least.
I'm gonna have to shrink between the molecules to get in there.
You can go separately. Go separate.
Hank Pym, founder of Pym Technologies. He doesn't know how Pym particles work. He lied about it, clearly, in Ant-Man. Or, you would think he lied about it. Unfortunately, this book ruined my life. I mean, it also proved that the timeline I'd been working on for like the past 4 years was correct, and everyone that corrected me was wrong, but I don't have any evidence of that because I never posted it properly. You're just gonna have to trust me on that one. Anyway, in this book, Marvel decides to confirm that what Hank Pym was saying about Pym particles was the truth. All they had to do was not say anything, and I could just live my life knowing that Hank Pym was lying in Ant-Man, and he doesn't know how they work. Yeah, unfortunately that's not the case. I've spent the better part of 3 to 4 months, aside from university work, trying to figure out how Pym particles actually work. They make no goddamn sense. Or at least they didn't. I mean, by the end of this video, you still won't understand how they work, but I have tried to get this to work with the laws of physics. It is stated that Pym particles increase density by reducing the distance between atoms while conserving force and momentum. This gives us a neat jumping off point. Because we know density is mass divided by volume. Density, mass, volume. That's not a P, that's a Greek letter rho. That's very important. In the case of Pym particles, and everything else, to change size is to change volume. For shrinking, volume decreases, and vice versa for growing. This works perfectly for constant mass. However, as much as they want to say it, mass is not conserved in a Pym particle based system. When Ant-Man shrinks, he clearly has less mass. When Ant-Man grows, he clearly has more mass. This is where the trouble begins. For shrinking, mass has to decrease. And we also know density has to increase. To make this equation work, volume must decrease at a faster rate than mass. To write this in another form, I don't know if you can, I'm gonna move. To write this in another form, differentials. Now don't worry, I'm not gonna go into calculus. Don't worry, we're not going into calculus. Even though this is very basic calculus. We're not, this is just demonstrate what I'm doing. We're not going into calculus. Obviously, this means that mass has to decrease with time, so does volume, but at a faster rate. We need to remember that force and momentum are constant here. And we also know that momentum, P rho, momentum equals mv, velocity, volume, velocity, volume. This is a little v, that's a big V. That is a P, that is a rho. Okay, and we also know that force times delta T equals momentum. Therefore, we can say that we know that force has to be constant, which means that everything else in this equation must change. So, we need to rewrite this. So now we have force times the change in time equals the change in mass times the change in velocity, where force is always constant. We are going to assume a specific time window. So this delta time is now a constant number, which makes this, that's not how you spell constant, I'm gonna leave it, that makes that constant. And we know that for shrinking, mass is decreasing, and if that's constant, this means velocity has to increase. So as you shrink, you get faster. Now we can check this works using the equation for kinetic energy. I should probably turn that projector off. You can see here, if mass decreases, this has to be constant. So if mass decreases, then that means velocity must increase to compensate. Okay? Okay. All of this seems to work out pretty well. Motion under the influence of Pym particles appears to follow conservation of momentum, which is a good thing. All it needs is velocity to increase to compensate for the mass, which would happen if momentum is conserved. Awesome. Unfortunately, we still have two main issues with shrinking. Number one, the laws of thermodynamics. If mass is decreasing, where does it go? And how is energy conserved? Problem 2, subatomic sizes. If Pym particles work by reducing the distance between atoms, how can you go smaller than an atom? Conservation of energy and nuclear fusion. Let's begin by assuming our total system energy U is as follows. U equals kinetic energy plus rest mass energy plus heat energy plus energy supplied by the suit's battery. Assuming the suit is a completely closed system, impermeable to energy, U will always be constant. We've also previously assumed that EK is constant. So, as we know, mass decreases, meaning the rest mass energy will decrease because the rest mass energy exists inside mass. So let's assume that this energy is converted into heat. So heat will increase. And the amount of power put in by the battery will be negligible. So we'll just pretend that doesn't exist. So, what is rest mass energy? Well, rest mass energy can be calculated using this equation you might recognize. Good old Einstein. He shows up later, by the way. You probably know that rest mass energy equals mass times the speed of light squared. Yeah, speed of light in a vacuum, to be more specific. If we are assuming that rest mass energy gets converted into heat, and total energy and kinetic energy are constant, we can write a new equation. The change in rest mass energy plus the change in battery energy, which we know is negligible, will equal minus the change in heat energy. Why minus? Well, that's because the change in rest mass is negative, but we need the change in heat to be positive because it's increasing. Therefore, we get the equation delta Q equals the change in mass times the speed of light squared minus the change in the battery's energy. This is where we need to add some parameters, because we know for shrinking, delta M is negative, and we also know that the battery can only decrease in energy when it's being used, so that also has to be negative. Now, we are converting mass into heat. What does that imply? Well, to me that sounds a lot like nuclear fission or fusion. We can safely rule out fission because Scott Lang is not a walking lump of cancer, so we'll go for nuclear fusion. I know that nuclear fusion also emits radiation like gamma and X-rays and UV, which can cause cancer, but don't worry about it, it'll all be solved later. Problem: how do you get nuclear fusion at room temperature? Answer: Pym particles must be a reaction agent for nuclear fusion. In the most common type of fusion found in the sun and what we're trying to replicate with fusion reactors, you get a hydrogen 2 atom plus a hydrogen 3 atom to produce a helium 4 atom plus energy plus some other stuff. I think that's a neutron. I'm not worried about that. With Pym particles, we're going to rewrite this. Fusion under Pym particles, we are going to initially model as energy supplied by the battery plus an atomic nuclei plus a Pym particle will produce heat and a new type of particle, which I will label as the Greek letter phi. This is an information particle. We are going to call this type of fusion Pym fusion. How have I been doing this for half an hour already? We are assuming that this new particle, the information particle, is the mass output of the Pym fusion process. Similar to how helium-4 is the mass output of a regular star's fusion process. An information particle will take up significantly less volume and has significantly less mass than the original nuclei. It also contains all of the information required to recreate the original nuclei it is replacing from scratch while maintaining the same charge as the original nuclei, in order to ensure none of the electrons are delocalized. For those who don't know, you have, this is a very simplified version. You have an this is your nuclei of an atom. It's where all your protons and neutrons are. And orbiting that, you have, you know, just a lot of electrons. This is an awful example. I'm doing this quickly. A delocalized electron happens when energy hits an electron and the electron just goes boop, and it is no longer tied to the atom. Do you want to know how cancer forms? Basically, when sufficiently high energy photons collide with your DNA's atom, an electron can be delocalized. This breaks your DNA. That's why the information particle has to ensure none of those are gone, because if any of those electrons disappear, you're fucked. And finally, assuming an information particle is created provides all the groundwork we need to grow back to normal size later on. So I'd say this just about shows that Pym particles are a reaction agent for nuclear fusion, a special type of nuclear fusion called Pym fusion, where you fire a Pym particle at an atom, it collides with the nuclei of the atom, destroying the nuclei, converting all that mass into energy, and then leaving an information particle. This information particle has significantly less mass, significantly less volume, holds all of the same charge, so holds all of the electrons of the initial atom. I am going to assume that it also condenses the electrons' orbits a little bit, so the atoms can get closer together. Okay, I'm gonna need my laptop for this bit. So, a process of Pym fusion would go something as follows for a box, just shooting Pym particles into a box. The suit battery applies energy to the Pym particle container, giving them a velocity and firing them into the box. Upon collision with an atomic nuclei, the Pym particle causes Pym fusion to take place. Heat energy and an information particle is created in this process. The suit lining must be completely impermeable to everything, including energy, so the heat energy is completely contained and no energy is lost to the surroundings. The heat energy is then collected by some mechanism in the suit for use later. This solves most of our shrinking problems. First off, if Pym particles work by shrinking the distance between atoms, how can you go subatomic? My first thought would be information particles are sufficiently small that you can go smaller than an atom. The problem with this is humans and living things. If information particles are so small, if you only shrink so far and not all the way, how would they interact properly with your atoms to do bodily processes? So they can't be too small. For life, we need our intricate systems of atoms and molecules to remain intact, to continue, well, living. Fortunately for Earth 199999, or 616 as some people will choose to call it, has fully accessible, fully manipulatable Einstein-Rosen bridges everywhere. And if you don't know what they are, it's just a wormhole. We also know that when someone goes subatomic, they enter the quantum realm. Now it is possible that the quantum realm is in fact not smaller than an atom, and is just a separate plane of existence, which is accessible through microscopic wormholes. These wormholes would be so small that normal atoms and fundamental particles wouldn't be able to slip through them. All of this implies that there is a specific size where someone is small enough to fit into one of these wormholes and enter the quantum realm. So now our new question is, what size? In order to make this work without just any random particle, molecule, atom, anything, just slipping into these wormholes, we need to assume either the wormholes are sufficiently small that nothing can go into them, or the information particles have such a specific property that allows them to enter them, whereas other particles can't. For obvious reasons, we can rule out option 1. This is because we've already just shown that you can't shrink smaller than an atom, and a lot of things are smaller than an atom, so you can't have a sufficiently small diameter to allow people in, but not atoms. What this implies is that at a specific ratio of information particles to atomic nuclei, you can now enter the wormhole. So now, an even newer question. What is this ratio? First off, let's find out the smallest a person has become that we can measure. The only object we have seen Ant-Man next to that we can physically put a size to is a tardigrade. At their largest, tardigrades are 1.5 millimeters in length, but can be as small as 0.05 millimeters, with the average adult tardigrade being 0.3 to 0.5 millimeters. We will take the average of the average, and we will assume that the tardigrade Ant-Man is next to is 0.4 millimeters in length. In the image that has just appeared on your screen, you can see the comparison. Now, doing some very rudimentary measuring, and that is putting my ruler against my PC screen and then taking a simple ratio of lengths, and then just assuming there's nothing funky going on with parallax or perspective, we get that Ant-Man is roughly 2/9 the length of this tardigrade. This allows us to calculate Ant-Man's size. So, the tardigrade is 0.4 times 10 to the minus 3 meters long. And we know that Ant-Man is 2/9 of this. This gives us a size of 1/11250 meters, which is 0.08 millimeters tall. We also know that at regular size, Scott Lang is 1.78 meters tall. We're going to add 5 centimeters to this to compensate for the helmet and the boots of the suit. So let's find the factor that he has shrunk by. We will do this by taking his new height and divide it by his initial height. This gives us 1/11250 over 1.78 plus 0.05, which is a scale factor of 1/41175. If you basically what this is saying is if you multiply his initial height by that, you will get that. You know what, let's try that right now. I'm going off script. Let's try this right now. So we know. So this is the shrinking factor. So if he is 1.78 plus 0.05 meters tall, we will times that by 1/41175. And that gives you oh shit. What did I do wrong? Hang on. 1/11250 divided by 1.78 plus 0.05. Oh shit. Glad I went off script. That's supposed to be a 2. I wrote that down wrong. Thankfully for all of us, I don't use this number in any math. It is just a number that's useful to know. So, alright, I'll make a note of that, and I will go and change the paper. This is what happens when you spend your late nights, early mornings, figuring out how Pym particles work. You miswrite a 2 as a 1. Anyway, we know somebody else that was next to our tardigrade. Hank Pym. Was he smaller or was he bigger than Scott Lang? Because if he was smaller, then we will use that because that will be our newest, smallest person. Using the same technique as before with this image on screen now, we get that Hank Pym's head... Okay, I haven't written it down in my notes, but I think I've just gone ahead and said that in this image, Hank's head looks to be about the size of the tardigrade's head. Okay, so now I've just double checked that. Some more stuff has appeared on the board. So this is correct. So Hank's height, no, Hank's shrinking factor, how much he is shrunk by in this image is about 5.32 times 10 to the minus 4. However, Scott's shrinking factor in this image is 4.86. That's clearly a smaller number, and so Scott has shrunk more. So now we know Scott is the smallest of the two of them, or at least got the smallest of the two of them that we can measure. And his shrink factor was 2 over 41,175. Not 1 over, 2 over. If we assume the human proportions are the same, which they are, this would give us that cubed for a volume shrink factor. So both of these images are taken pretty much immediately before the two go subatomic. So we now can approximately say that 2 over 41,175 all cubed is the smallest shrink factor you can get to volume-wise. Now from here we're going to pull a physicist, because I am one, and we're going to assume that every human is a cylinder. And to create this estimate, we are going to first find Scott Lang's torso volume as a cuboid, assuming that his bicep diameter is the side of his torso. Now, I don't know how they found this out, but someone has found that Scott Lang's bicep diameter is about 0.1132 meters. And so that's going to be our torso depth. 1/3 of the average height of a human is their torso. So the height of this cuboid will be 1.78 over 3. This is approximately 0.593 meters. The average male adult of 1.78 meters height will also have a torso width of approximately 0.445 meters. This gives us all of the properties we need to calculate the volume. This would be V of torso is 0.1132 times 0.593 times 0.445. This number gives us a volume of approximately 0.2 2987 meters cubed for the torso. Now, why did we calculate the volume of Scott Lang's torso as a cuboid? Obviously, this was to find the radius of the cylinder. Because we know that a torso is 1/3 of someone's total height, we know that the torso in our cylinder model will just be 1/3 of the cylinder. So what we can do is we know the volume of a cylinder is no it isn't. We know that the volume of a cylinder is pi r squared times height. This allows us to calculate the radius of a cylinder by simple rearranging, which would be v over pi h. Plugging in the numbers to this equation will give us the radius of Scott Lang if he were a cylinder to be 0.1267 meters. What we can do now is map this radius to his entire height. So we know that Scott Lang's initial height is now pi times 0.1267 squared times his height of 1.78. This gives us a volume of approximately 0.08697 meters cubed. I think I remembered that correctly. No. 8976. No. 8967 meters cubed. And we know that the volume shrinking factor is 2/41175 cubed. This is going to change the answer. Okay, so I've redone the calculation with the new shrinking factor that I calculated, the correct one. It's like a magnitude of 10 off what I calculated in my notes. This is the only time I ever used the shrinking factor in an equation, so it shouldn't affect anything, hopefully. Fingers crossed. Calculating his new volume, therefore, is 0.08967 times 2/4175 cubed. This gives you approximately 1.028 times 10 to the minus 14 meters cubed. So now we have our initial and final volumes. Obviously the next step would be to find his initial and final masses. Well, the problem with that is to find his final mass, we would first need to find how dense he... I'm pretty dense. In order to find his final mass, we need to figure out how much density has increased. We can't do that here because we need final mass. Lucky for us, there is another instance of him shrinking where we can calculate his final mass. What is this other situation? Well, Scott Lang frequently shrinks down to about the size of an ant so he can ride a black carpenter ant, as can be seen in this image. The average black carpenter ant is about 13 millimeters in length. We can see from this image that Scott's height is about a 2/3 ratio with the carpenter ant's length. So here, Scott's final height is 2/3 of 13. This is about 13/3500 meters. It's not simply 26/3 because that's millimeters and we are working in meters, so I've done the conversion between steps. So let's find the ratio between the final height and the initial height. That would be 13/1500 divided by 1.78, which gives you 13 over 2670. With no units, because it's a ratio. So now we have the scaling factor. We know that Scott Lang's bicep is 0.1132 meters at regular height. This means we can calculate a new one, which gives us his torso volume to be approximately 3.45 times 10 to the minus 9 meters cubed. This now allows us to calculate his new volume for his new shrinking to be approximately 1.03 times 10 to the minus 8 meters cubed. Okay, so we know his initial volume, we now know his final volume. So, a black carpenter ant can carry about 7 times its own weight. The ant doesn't appear to be straining, so I'm going to say Scott Lang is about 6 times the weight of the ant. A black carpenter ant's mass is about 17 times 10 to the minus 6 kilograms. This puts Scott's final mass at around 1.02 times 10 to the minus 6 kilograms. Minus 4. 10 to the minus 4 kilograms. Okay, so now we have a final mass, a final volume, and we calculated the initial volume earlier. All we need now is his initial mass. The average density of a human is 985 kilograms per meters cubed. And of course, we need to remember that density is mass times volume.
That is a P, that is a rho.
Would give you density over volume.
That is a P, that is a rho.
No, that's wrong. And rearranging an equation we brought up earlier gives us mass is density times volume. We know his initial volume, and we know the average density of a human being. This allows us to calculate his initial mass. So, let's find out his initial mass. So, initial mass will equal 985 times 0.08967. That gives you approximately 88.32 kilograms. That's not too bad. What this means is we finally have initial mass, initial volume, final volume, and final mass. This allows us to calculate a ratio between them. The mass-volume ratio parameter. So, we know that this ratio of final mass divided by initial mass is in some way proportional to the final volume over the initial volume, because they both decrease. We know that this side decreases faster than that side, so simple proportionality calculations give us a constant. This constant I will call the mass-volume ratio parameter. If we want to know what this constant is, we simply plug in everything we know and rearrange to get omega. So, if we want to find omega of a human, we can simply plug in all of those numbers. And we have all of those numbers. So this gives us a value of 10-ish. Now, why is this specific to humans? You'll see later. It's complicated. It's stuff to do with the atoms you're made of, the materials. It's different for everything, and the average human's going to have about 10 for this constant. So, now we know what this parameter is. We can go back to the initial example where Scott Lang is at the shrinking limit. What we wanted to know was Scott Lang's mass. Well, lucky for us, we don't need to know how dense he is anymore, because we now have a handy parameter. Doing some quick rearranging, what we want to know is final mass. To get that, we simply do omega h times initial mass times the ratio of volumes. Plugging in all of our numbers gives Scott Lang a mass at the very smallest you can possibly be to be about 1.266 times 10 to the minus 11 kilograms. Now that is small. Now what we want to do is just double check everything. So what we know so far is that density has to increase where mass and volume both decrease. So what we now need to do is calculate his density after he's shrunk, and then compare that to the average density of a human. So we know that the initial density is 985 kilograms per meters cubed. What we need to find out is the final density. Lucky for us, that is simply the final mass over the final volume. We have just found the final mass. Plugging these numbers in gives us 9,855-ish kilograms per meters cubed. We have successfully discovered that rho f is bigger than rho I. The final density is bigger than the initial density. Therefore, we have successfully got a shrinking system that increases density while decreasing mass and volume. So what was all this for again? It was to find the ratio between the number of information particles and number of atoms. If you'd like to see a more in-depth analysis on how many atoms of each type and how much mass is in Scott's body, then you can go read the paper. I've put a link to it in the description below. For simplicity and time's sake, and so I'm not spending the next half an hour doing maths on this board, I'm just going to skip the process. So my maths shows that the number of atoms initially in Scott's body is approximately 8.32 times 10 to the 27. And then doing the maths again after he's shrunk gives me a final count of normal atoms to be 1.30 times 10 to the 15. That's a significant decrease. So this gives us a number of information particles to be the initial amount minus the new amount of atoms, which gives us approximately 8.32 times 10 to the 27. Yes, this number is too small. This number of 10 to the 15, this number of 10 to the 15 is too small to impact this number. All of this was to find the ratio of information particles to atoms. So let's do n phi over na initial. Well, that gives you 0.9999999, and so on. There are some other numbers at the end of the nines, but I think what we've discovered is that to enter one of these Einstein-Rosen bridges or wormholes into the quantum realm, your n phi over na has to be 1. In other terms, to enter an Einstein-Rosen bridge into the quantum realm, you need to be made up of entirely information particles, and nothing else. So in summary, what we have found so far is that Pym fusion causes information particles to be created and the original nuclei to be destroyed. The information particle holds all the information needed to recreate the original nuclei, while also containing all of the charge needed to hold all of the electrons still in place. When your ratio between information particles to number of original atoms tends to 1, you can slip through an Einstein-Rosen bridge into the quantum realm, and that is how you go subatomic. We've also discovered that there is a parameter called the mass-volume ratio parameter that describes how a specific type of object will change with mass and volume when it shrinks or grows. These are specific to objects, so we calculated the human one. If you'd like me to prove why it's specific to a different object, feel free to read the paper. I have like 2 pages on calculating the same parameter, but for the shrinking building from Ant-Man and the Wasp. So, we've solved the problem of going subatomic. The new problem, what the fuck happens to all that heat energy? So far, we've been assuming that all of the rest mass energy gets converted into heat during the Pym fusion process. But where does this heat go? We know for a fact that the wearer of the suit doesn't boil alive when shrinking, so it has to go somewhere. So I think our first idea is to calculate exactly how much heat energy is generated when you shrink to the shrinking limit. We can actually really easily calculate this. It's Q m initial c squared plus the energy of the battery. Now, that is negligible. This is a very small amount of energy. You will see why I'm ignoring it in a second. So, we know the initial mass is about 88.32 kilograms, and we're going to times that by the speed of light in a vacuum squared. In my notes I use a better value of the speed of light, it's fine. This gives us an approximate energy of 7.94 times 10 to the 18 joules. Shit. That's a hell of a lot of energy. This is why we can assume the battery is negligible, because there is no way a battery is going to be able to produce that much energy. A battery. We also know that Scott isn't instantly vaporized upon shrinking, so I think we can safely assume that the energy is in fact not heat and is stored somewhere. So instead of heat energy, I'd say the easiest places to store energy would be chemical or potential. Now, I don't have the expertise to figure out how potential energy works, so we're gonna say all of this is chemical energy. Usually, chemical energy comes in the form of the bonds between atoms, and breaking those bonds releases the energy holding them together. What we're going to do is we're going to introduce a new property of information particles. Because information particles are very nearly massless and very nearly volumeless, we're going to say that obviously they carry the same charge as the original nuclei, but we're going to say that because they are so small and the electron orbits need to go from like that to a new orbit very close, that all of this energy here gets transferred into the information particle so it can hold the electrons. That's a bond. There is a bond between the information particle and the electron, and that's where the chemical energy goes. So what this means is we have a new Pym fusion equation. We have the energy from the battery plus an atomic nuclei plus a Pym particle produces an information particle plus the chemical energy stored within an information particle. Now obviously all of that energy is not going into a single information particle. That is being spread across the 10 to the 27 information particles. So each information particle doesn't actually need that much chemical energy to hold the electrons. This works. What this also means is our energy equation is now the energy of the battery plus the rest mass energy equals the chemical energy stored inside the information particles. And that about covers shrinking. We are done. We now know how it shrinks, where the energy goes, that momentum is conserved, and how small you have to be to get into a wormhole, and why atoms don't go into wormholes, because you have to be entirely made of information particles to enter. Okay, let's say Scott Lang is at the shrinking limit. All his atomic nuclei have been converted into information particles. All we need to do is use the information particles to create mass. The most obvious case of creating mass from energy that I can think of is pair creation, but that requires a matter and antimatter pair to be created, and we don't want a whole lot of antimatter to be created, because that's a waste of mass that we're not using. So, I think we're going to create one from scratch. As can be seen when the suit enlarges, they swap out which type of Pym particle they're using, most of the time. When shrinking, they usually use the red Pym particles, and when growing, usually use the blue ones. This implies we actually have two types of Pym particles, a shrinking Pym particle and a growing Pym particle. These will be labeled PS and PG accordingly. When the wearer of the suit wants to grow, they will simply do exactly the same as they do for shrinking. They will initiate a mechanism that fires growing Pym particles into the suit. Now, we are going to assume that growing Pym particles are very strongly attracted to information particles, and that they will dodge any atomic nuclei in their way. This solves a problem later, so I will draw a diagram. A growing Pym particle, which is going this way. And we have our information particle. But in the way, we have an atomic nuclei. What will happen here is, for anything to work from this point onwards, the growing Pym particle has to travel like this, following this line. I can't avoid it. I have tried. It has to, for anything to work from this moment forward, they have to collide with every information particle before the normal atomic nuclei. Upon collision with the information particle, both the growing Pym particle and the information particle will be destroyed, releasing energy. This energy won't actually be released. It will be used to reform the mass of the original nucleus. Because the information particle is very specific and only contains the information required to recreate that single nuclei, when the growing Pym particle and the information particle collide, The energy reforms itself using the information from the information particle to recreate the original nuclei. Yes. Luckily, we don't have to do any maths for this. If there are information particles present, that means you've previously already shrunk, which means that it's simply a reversal of the shrinking equations. Hooray! Now we can move to growing bigger than your original size. So, so far, we've described how growing would work if there were information particles present. If you are growing bigger than your original size, you have no information particles present. That means we get a new line. This new line is just that. What happens when they collide? The original atomic nuclei has to remain, but mass increases, which implies that a new atom has been created. This won't actually be a new atom. This is going to be another type of information particle. I will call this particle a massive information particle. That is because when you grow, your mass increases. So the mass of this new information particle is non-negligible, like the original. So it's a massive information particle. Anyway, let's calculate the mass of a massive information particle. Okay, first things first. So we have an information particle, which is represented by Greek letter phi. That is an awful phi, but I'm not changing it. A massive information particle will be represented by a Greek letter psi. I drew that really weirdly. I don't normally draw it like that. Let's try that again. A capital psi. This is a massive information particle. That's just getting some notation out the way. Yes, this requires notation, if you haven't guessed already. Now, if we want to find the mass of a massive information particle, we can actually do this quite easily. We simply take the inverse of the mass-volume ratio parameter equation, because flipping it just equals growing instead. So, we have the initial mass over the final mass is 1 over omega times the initial volume over the final volume. That's quite simple. Now, we know from Ant-Man and the Wasp that Scott Lang was able to achieve a final height of 65 feet, which is 19.812 meters. And we know that his initial height is 1.78 meters. Do you know where this is going? It's growing factor time. So our growing factor will simply be HF over HI, which is 4953 over 445. And obviously this means our volume growing factor is 4953 over 445 cubed. Simple enough. Now you may be wondering where I'm going with this. If we have an initial mass, and that is smaller than our final mass, then that means we've added mass. All of this added mass is going to be the mass of massive information particles, because you can't create mass any other way in this situation. So, what we want to do is we want to use this equation to find the final mass, and then using that, we can then find the mass of all of the massive information particles added together. And then all we need to do is find out a way to figure out how many massive information particles there are. And doing that will allow you to divide through and find the mass of a single massive information particle. But I'm jumping ahead. Let's continue. Now we have the volume growing ratio. This allows us to calculate VF to be 0.998 meters cubed. Now, this is actually really simple. We simply rearrange this equation. So we'll get MF equals omega VF over VI MI. And we know everything on this side. That's so convenient. This gives us a final mass of approximately 9835 kilograms. This means that the mass of all the information particles is approximately 9747 kilograms. So, how much energy is needed to create this mass? That's simple. That's another E equals mc squared. That gives you 8.76 times 10 to the 20 joules. What the fuck? For comparison, the sun, the sun emits 3.83 times 10 to the 26 joules per second. Not all of that comes to Earth. So you can't. So to grow 65 feet tall, 19 meters, you need 8.76 times 10 to the 20 joules of energy. Where the fuck does Hank Pym get this from? First port of call is we have the battery. The battery. The battery, which is small enough to fit on a belt buckle, presumably. We've already assumed it's negligible, so we can already rule out the energy from the battery. My proposal here is that a growing Pym particle contains the energy. So if this amount was split between every single growing Pym particle, it could work. Unfortunately, we need to calculate how much energy each growing Pym particle actually has. And to do that, you need to calculate how many growing Pym particles get you that much energy. So how many? Let's assume that we have our original mass. And for our original mass, you have a ratio of massive information particles to normal atoms. For normal mass, you have 0 massive information particles, and you have 1 lot of your normal atoms. Okay, let's assume if you double in mass, you now have the exact same amount of massive information particles as you have normal atoms. That means there is a 1-to-1 correlation between how much mass you have and how many individual particles you have. Because for 2 masses, you have 1 lot of massive information particles and 1 lot of atomic nuclei. That gives you 2 lots of your original mass. So that means if you were to go 3 times your original mass, well, you can't gain any more atomic nuclei. So that's still 1. But what you can gain is massive information particles. What this means is you have a correlation where the number of massive information particles will equal the ratio of masses minus 1 all times the number of normal atomic nuclei. Yeah, you may remember we already know how many atomic nuclei Scott Lang has, because we needed that number earlier. You will also know we have these two masses. This means we can actually calculate our n psi, which is slowly getting worse and worse to draw. This n psi will actually equal 9.19 times 10 to the 29. That's a lot of particles. What this means is that the mass of a massive information particle is the whole mass we calculated earlier divided by that number. So the mass of an individual massive information particle is actually only 1.06 times 10 to the minus 26 kilograms. That's a small mass. You see, now we know the mass of 1. We can plug this back into E equals mc squared to find out how much energy is needed to create a single massive information particle. Doing this calculation gives you 9.53 times 10 to the minus 10 joules. That's suddenly a lot more doable. What this implies is that each growing Pym particle contains that amount of energy. Upon collision with an atomic nuclei, it creates a massive information particle of mass 1.06 times 10 to the minus 26 kilograms, which also behaves exactly like the nuclei it derived from. That way, for example, if you were to grow a muscle, all of the massive information particles would act like the muscle and would increase your strength. So you could say, perhaps, walk under your new weight. Now, obviously, Hank Pym still needs 8.76 times 10 to the 20 joules of energy to create the amount of growing Pym particles needed to grow by 20 meters-ish. How? Well, he has had decades to slowly create these particles, so he's probably got enough energy over the decades, but he's going to go through these really fast. A solution's going to come up later. Alright, the last step. Now we need to shrink back to normal size. Remember that diagram from earlier, where the growing Pym particle dodged the atomic nuclei to hit the normal information particle? Imagine that diagram, but it's now the shrinking Pym particle dodging an atomic nuclei to hit a massive information particle. Yep, that's right. If we want to shrink back to normal size, we're going to have to assume that shrinking Pym particles are similarly strongly attracted to massive information particles, just like how growing Pym particles are strongly attracted to normal information particles. So, the shrinking Pym particle collides with the massive information particle. They destroy each other. Your mass decreases. You would think that would be it, but remember that energy, 10 to the 20 joules? That's now released again. And it needs to go somewhere. And we seemingly don't have anywhere for this energy to go. Yeah, that's where I got stuck for a while. I got stuck at that point for a very long time, actually. What I propose is this energy is reabsorbed into the suit. The suit then uses this energy to recreate growing Pym particles. That way, once you've made your first batch, you almost have a continuous supply. Obviously, this creation of growing Pym particles won't be 100% efficient, neither will the energy collection. So you're not going to get the same amount you get back, but you're still recuperating some of your losses. And due to shrinking Pym particles not actually needing their own energy, they seem to be much easier to create than growing Pym particles. And therefore, you can go and create as many shrinking Pym particles as you want in a lab, but the growing Pym particles are really difficult. So if you have a system to start remaking them inside the suit after you shrink back down to normal size, you're good. And that's my proposal. When you shrink down, the shrinking Pym particle and the massive information particle collide, they destroy each other, and the energy gets absorbed by the suit and is used to recreate some growing Pym particles. So you can grow back to whatever size you want to that's bigger than your original size. And that's it. We're done. In this video, however long that I've taken, we have successfully discovered how Pym particles work. Now all I need is for the MCU to not mention it again, because I've put far too much work into this. All this speaking of density, and I'm the densest. That was such a stupid fucking joke. If you want to go more in depth with this maths and see all my references and just an actual summary page of all the discoveries, then there is a link to download my fake jokey paper in the description. It goes through everything. Every step I've done, it goes through. There are probably a lot of typos because a lot of this work was done at like 3 a.m. Yeah, cool. Thank you all for watching this video. This is the first video I've ever done like this, so I hope you enjoyed it. Yeah, I'll see you in the next video.